Hello, everyone. Welcome to the third lecture of functional programming using Koch theorem prover. My name is Mukesh, and I'm a senior research associate at the University of Cambridge. In today's lecture, we are going to explore natural numbers. So without a further ado, let's get started. Before we start, how to encode natural numbers? What is natural number? So natural number is 0, 1, 2, 3, so forth and so on. And what are the operations on natural numbers? We can add them. 1 plus 1 is 2. We can subtract them. We can multiply them, and we can divide them. So that's the operations on natural numbers. What properties they follow? So we'll come to these properties. We'll prove the properties of natural number in this video, in this lecture. So let's get started. From the previous lectures, we know that how do we encode data type? The keyword is inductive. Then we give it a name. I'm writing as nat as a short form for natural number. And I'm now saying that it's of type. So Koch is based on type theory, and everything has to have a type. I'm not going into more details of these type theory, but if you are interested, just let me know and I will find a more capable person than me, and I'll post another video about type theory. But in this case, I'm saying that inductive nat colon type. So nat has type. And now I am going to give constructors. Using that, we can build the terms of type nat. So my first constructor is O. It represents 0. O represents 0. We interpret O as 0. And now the next constructor, I'm going to say S, which takes a natural number and returns a natural number. So what this constructor symbolizes? Well, this one says that if you give me a natural number, then I will give you the next natural number. So let me demonstrate what I mean. So 0 is represented as O. 1 is represented as S of O. 2 is represented as S of O. So you can think this is our base case. This is where we're starting. And then if we wrap it in S constructor, then we get a next natural number. For example, here we are wrapping 0 in S, and then we are getting S of O. That symbolizes, that represents 1. S of O represents 2. So this is the model of natural number in Koch theorem prover. What else can we do with this natural number? A moment ago I said we can add it, we can subtract it, we can multiply them. So let's define a function to add two natural numbers. So far we have seen this used keyword definition. So let's use that. Add nm of type nat, and it returns nat. So what this function is, add takes two parameters, n and m of type nat, and it returns, and the return type is also nat. So I'm going to do match n with, so match with pattern matching on n. Remember, n has two constructors, so I need to write two clause. So when n is 0, 0 plus m is m, so I'm going to return m. When n is successor of some number, here n prime, then I'm going to take the s, add the rest of the terms, and oh, we get error here. So what is the error here? So it says the reference add was not found in the current environment. So this is our first learning of the day. When we define recursive definition in Koch theorem prover, the keyword is fixed point. So if you have a recursive definition, then rather than using definition keyword, we need to use fixed point. So now Koch is happy. It has accepted our definition. So let's do a bit tinkering here and see what would happen if I just pass the same n. Okay, so now it says that cannot guess decreasing argument of fix. So what Koch here rightly complaining that it cannot guess the decreasing argument. So remember, Koch is not only a functional programming, but a theorem prover. And every function in Koch needs to terminate. How Koch is measuring the termination here? Well, previously I was passing n prime, so it's the smaller version of n. I'm taking the s out and then passing a smaller argument to the rest of the function. If it's this one, we know that then it will go in a loop. We can do that using cofix point, but that's not relevant here. And that's probably more technical. But here, when I'm just passing n, it's complaining, no, I cannot guess, Koch cannot guess the argument. So that's the second learning. Every function in Koch, when we encode it, it has to terminate. The type checker should be convinced that yes, it's a terminating function. So I'm going to make the bring n prime here. And now Koch is happy. So far we have inductive definition, and we have a function to add two natural numbers. What else can we do? Well, we can evaluate this. So eval compute in add. And what would happen if I add 0 and 0? Okay, we get 0. What would happen if I add 1 to 0? So we should get 1. And remember, the representation of 1 is S of O. So here we should get S of O. We get 1. What would happen if I flip the argument? Well, 0 plus 1 is also 1. So that's our first property of the day, that addition on natural numbers are commutative. Means it does not matter if I add n plus m or m plus n. It should be the same. So order should not matter. But before we go and prove this theorem, let's prove some simple theorems. And I'm going to call them lemma. So lemma is a way to state a theorem, and I'm going to name it name. Now I need to give it a name, so I'm giving it add O. L stands for left. For all n of type nat, so every n of type nat, and remember, how can we construct an element of type nat? Either using this constructor or using S constructor. Add On is equal to n. And let's prove this. So I'm going to assume intros n. What I mean is I have moved n from goal to assumption. So now I have an arbitrary natural number n. What can I do? Well, let's see. Let's simplify this and see how it. Okay, this is good. This is a good thing. And now we know that our tactic reflexivity and QED. So this is our first proof with natural numbers. So let's change it a bit. Now I'm going to prove another lemma, but this time for every n of type nat, NO is equal to n. So this lemma says that 0 plus n is n, while this lemma says that n plus 0 is n. And we know that it's a true statement. So let's prove this and see how it goes. Prove intros n SIMPL. Oh, it's not simplifying anymore. If you remember here, but here nothing happening. So this is another learning of the day. In this case, if you look, the function definition, it's decreasing on the first argument. So let me rename this. And then we can see what's going on. So you see here, when it's 0, this function goes here and immediately returns m, and this thing simplifies to m. While if we look at this thing, there is no pattern matching on m. So this function is not simplifying. Now I can write another function that is same as add, but it does pattern matching on m. In that case, this lemma can't be proved by just simplification, while this can be. So let me do that. I'm going to write fixed point add r nm of type nat, And rather than pattern matching on n, I'm going to pattern match on second argument, which is m. So if m is 0, n plus 0 is n. And if it's Sm prime, then I give S add R n m prime n. And my claim is, now if I replace this with add R, this simplification will not work. And the reason is that now we are not doing pattern matching on first argument, but on second argument. So we are not touching n here. So the code, the simplifier or the type checker has no idea how to reduce the term which is 0. So let's prove this thing and convince ourselves that it's true. So I assume, oh, you see, it did not. It's not reducing at all. So let me admit this. So admitted is a keyword where you tell Coq theorem prover that, believe me, this theorem is true, and I'll come and prove it later. However, we should be very careful with admitted, because it's quite possible that when you are not very experienced, you may assume which is something false and then develop your whole theory, but then your whole theory is resting on a false assumption, and then you can't prove this and your development just crumbles. So you should be, when you admitting a proof, you should be very, very careful. Convince yourself that it's true, then you admit it and move on to the next proof. So here I admit, and now I'm going to say that my claim is that now it can be simplified. And lo and behold, it did. Reflexivity and QED. So we can see that based on our definition, how we can prove theorems by simplification, at least at this point. So how definition matters. And when you'll become very expert in theorem proving, you will craft your definition in such a way that the proving theorems are easy. So that comes with experience, but in this case, this is the first demonstration that there are two definitions. One definition helps in proving one theorem, and other definition helps in proving other theorem. So you see how definition matters. Okay, so let's get rid of this. And what I am going to do is, let's stick to the definition we have and QED. So let's, using the same definition, we prove this lemma. Okay, so the things we have learned from the past, we can do intros n, means I have assumed an arbitrary n in the context. Destruct n. Okay, so destruct n split into two cases. So destruct n intros n assumed, and when I'm doing destruct n, it's the first constructor O and the second constructor S. See here, the only problem is that it's naming this this thing as n. So if that's making you uncomfortable, you can say that destruct n as, and then you call here n prime. Okay, and now you see that it renamed it. Or maybe more better, you just do a simple intros pattern. So you saved few keywords here. It did all the pattern matching while introducing the term. So it's you can save few keywords here. But let's prove this. Let's see. I can do SIMPL and reflexivity. And if you look at the goal here, I have nothing in this at the top of this line assumption that helps me in proving this goal. If somehow by magic I get an assumption that this thing is equal to n prime here at the top of line, then I can replace this thing by n prime and these two terms are equal. But I don't have. Now, what I can do is, okay, I can destruct again n prime as let's say n double prime. And I can do simplification and reflexivity. But the other case, we are still at the same. Now I have this thing, successors, but I have nothing in this, in the assumption. If you are in this situation, it's a good hint that you need to induct. So let's see how would we prove that. So I will say induction n. The first thing is simplification. So it's the same as the previous destruct, reflexivity. And now you see here, we have an equation. We call it induction hypothesis, which says that if you add n plus o, then it's equal to n. And our goal is to prove that so we get to assume that for any arbitrary natural number, n plus o is equal to n. And then we need to prove that n plus 1 or 1 plus n is equal to 1 plus n. Okay, so we do simplification. And now I need to replace this by this term. So let me first rewrite the tactic. Rewrite IHN. See. So when you say rewrite and then you have equation where terms are equal, what this means is the Koch theorem prover is going to look at this equation and will look for the left-hand side of this equation and search for that term in the goal. So let me change it a bit. So rewrite IHN, the Koch theorem prover is going to look for the left-hand side of the equation in the goal and replace all the occurrences here of that left-hand side in the goal by the right-hand side of the equation. In this case, the left-hand side is just appearing here. So it will replace this by n. What would happen if I rewrite other way? Means I'm telling Koch theorem prover to look at this equation and now take the right-hand side of this equation and search for all the terms in goal, which is here and here, and replace this by left-hand side. So if this rewrite is going, if this rewrite successfully rewrites, then this n would be replaced by add no, and this n would be replaced by add no. So you see, you can rewrite both way of equality, but which way you write depending on your situation. But this is how rewrite works. So in this case, it's not very helpful. We'll get rid of this. We'll rewrite. And now we have reflexivity and QED. So far, we defined natural number, we defined addition function, we proved two lemmas, that O plus M is equal to M and N plus O is equal to N. And this is the first time we introduce induction. If you want to see the proof, let me show you the proof term. So internally, we are building Galena terms, which would be very difficult to build by hand. But maybe in next video, I'll try to write these proofs using refined tactic. But for the moment, let's stick to our normal induction proofs. Okay, so now that we have proved these two, let's prove the commutative lemma. So add com. So lemma is a keyword to state your theorem. Add com is the name, colon, and then you give them type, or you express your logical statement. In this case, I'm going to say for all nm of type nat, add nm is equal to add mn. Okay. Now I can do intros nm and destruct nm, and you go and convince yourself that it will not. You won't be able to finish the proof. One way to look why destruct would not, because now we are dealing with inductive structure and recursive functions. So you need to think more in terms of induction and recursion, that if you get a small instance, can you prove it for bigger instance? So let's do that. Let's do induction n. Now, why I'm doing induction on n? Because I could have done induction on m, but I'm doing on n because it's just for convenience, and the add function is defined decreasing on the first argument here, but that's not a very genuine or very valid argument. You could do it on m as well, because m here appearing as a first argument. So you go and try by doing that induction on M. So let's see induction N, and I am going to intros M. Then I do SIMPL. Okay, and now I need to prove that M is equal to M plus O. But we proved this a moment ago, which is this lemma. Add underscore O underscore R. Except there is a just slight problem. On the left hand side, we have add NO, while here we have M. So what I can do is I can just massage our goal by tactic called symmetry. So equality is symmetric and the tactic is symmetry. So you can A equal to B and then you apply symmetry, then it will become B equal to A. Okay, so now here there are few ways to prove this goal. So let's go one by one. So one tactic is apply. And now I'm going to apply this lemma to this goal. Okay, so this is going to unify with M. N is going to unify with M. And I already have M here, so it would go away. Add OR. And you see there is no more goal left. I can do, if it feels very magical to you, here is, you can see what's going on. Post proof M as HM. So this thing is, I'm renaming this thing. You can just write simply post proof, but it's not a good practice because Coq replaces with some ad hoc names and maybe later it will become a problem if your proofs are big. So I'm going to call it HM. And then I can say that it's exact the same term as HM. You can also say that it's assumption. Other way to prove this is rewrite. So if you look at this thing carefully, it says that add NO equal to N. Now, if I do somehow, if I replace this by M, then I can use reflexivity to prove that thing. And we already know that rewrite add OR. So now what I'm going to do this, rewrite add OR. So this is an equation. You can see here it's an equation. Now what Coq theorem prover is going to do for me is going to look for this term in goal, which is this, and replace it by M. Well, in this case, it's M. Okay. If you're confused by N and M, you can think that I'm instantiating N with M. Okay. But I can't do this because see, there is no N here. So I am instantiating this N with this M. Right? And now I can do reflexivity. So depending on your preference, I prefer apply because it's just one few keystrokes, but it depending on your preference, you can go either way, apply, post proof, or rewrite, and then reflexivity. So let's go for the next proof, and then I do intros M, and I do simplification. So let's see, what do we have here? So I have an arbitrary natural number n. I have an induction hypothesis which says that for all m, so you can think of this as a, well, it's a dependent type. So you can think of IHN as a function that takes a natural number, here it's m, and then it gives you a proof that these two terms are equal. So it's a way, that's how I think IHN is a function, and then that takes a natural number and returns a proof that add nm is equal to add mn, right? So that's what we have in our assumption. What do we have in our goal? The goal is I need to prove add nm is equal to add m. So we need a lemma. There is nothing that we need to pull out this successor from this add function. So what I'm going to do for the moment is I'm going to admit a lemma, which I'll prove later, but for the moment I'm going to admit it, and I'm going to say add sn for all nm, or if you nm add n s of m is equal to add is equal to s add nm. Okay, and proof and admitted, right? Now at this point, if I replace this thing by s add mn, then I can use this induction hypothesis. So what I mean, let's first rewrite this thing. So what it means, Coq is going to look for the left-hand side of this equation in the goal, and then replace it by the right-hand side of the equation. So there we go. And now if you see our induction hypothesis, it says that for all m, add nm is equal to add mn. So I can replace this by this, and it's again the same rewrite and reflexivity. So one more thing you can do is you don't, if you're in this kind of situation, you just put a comma and then see, it's all happening in one step. So this rewrite and this rewrite. So that's another trick. If you are doing rewrite, 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 then you put a comma and then it will rewrite in one go. And reflexivity and QAD. So far, so good. Now I'm going to demonstrate a trick here. I'm going to show you something. So I'm stating my theorems in such a way that I'm thinking ahead of the time, and I am keeping the proof term, the term which I'm going to induct at the very beginning. Now, why I'm doing that? Let me show you. If you look at this induction hypothesis, I get this for all m quantifier in induction hypothesis. And this is very crucial because it's a very, very general induction hypothesis. It's very strong. You can do many things because you can instantiate this M for various values, depending on what natural number you have in your context. So I have N and M, and I can instantiate this, say hypothetically, I can instantiate it post proof IHN with N. So I get term add N equal to N. This is not very valuable, but I'm demonstrating why it's crucial, because sometimes in future, you may need your induction hypothesis very general. What else I can do with IHN? Well, I can instantiate this with M. And now I can do that rewrite H here. So I'm going to prove it in another way, and then we'll see that induction hypothesis is not as general as this much. However, my proof would go through. It's not going to matter in this case. But in future proofs, sometimes it becomes very crucial that how you do induction and how you keep your induction hypothesis as general as possible. So I'm going to assume NM, and then I'm going to do induction N. So the first one, I'm going to admit this. And now if you see here, it's not general anymore. I cannot do anything, the thing I did post proof IHN. You see, it can't, it's illegal application, non-functional construction, because IHN is no longer function. It's now a term. Now it can't be, it's a term, and it can't be applied any argument. So you need to keep these things in mind that you should try to keep your induction hypothesis as general as possible. So let's finish this proof using this way. So SIMPL and symmetry, and then I'm going to do apply add OR, and then again SIMPL rewrite IHN and reflexive. Okay. Reflexivity is not going to work, so I need to rewrite this lemma. Oh, here it is. Let me copy paste. So in this case, it did not matter. We assumed both natural numbers and then we induct on N. But this example clearly demonstrates that the difference between the induction hypothesis in two cases. In one cases, you are not getting for all quantifier. In another case, you are getting. And as a theorem proving person, you should favor on getting your induction hypothesis as general as possible, means having for all quantifiers is always good. It's a more general, and you can do more things with for all quantifier than without it. So I'm going to get rid of this. And I'm going to stick to our proof where we get stronger version of induction hypothesis. What else I want to demonstrate? So one more trick I want to demonstrate here is, as I said, I'm thinking ahead of the time and writing that the term at the very first place, which I'm going to induct, but what would happen if I do this? And I want to do induction on M. Oh, sorry, N. So I can do intros MN, and then the keyword is revert M. So you see it pushed M into the context, and now we proceed as, see, our induction hypothesis is now general. Another one is more stronger, is generalized dependent M. So this works based on my experience all the time. And then your proof is the same as the previous step. So nothing different. So these are few steps. So the key takeaway from this lecture, if you really want, focus on making sure that your induction hypothesis is as general as possible. Don't assume everything in the context. No, assume only that part which is needed to induct, to take a step in the proof, and then leave everything else in the code. So far, based on my experience, it works. It has worked very well. And hopefully it will work for you as well. So let me prove this thing. Well, I'm going to now just do induction on N. I'm not going to assume M. You know why? Because I want to keep my induction hypothesis as general as possible. Okay. It's not going to matter in this case, but since I'm doing these lectures and I want to put these ideas I want to make these ideas more explicit. So intros M, then I do SIMPL, and reflexivity is good. I'm going to do intros M, SIMPL, and let me look if I can replace this by something like this. So if you look at our induction hypothesis, it says that add NSM is equal to this thing. So I am going to do rewrite IH N and reflexivity should do that job, QAD. So today we learned natural numbers, how to add them, how to prove natural number is commutative. And in the process, we learn how to keep our induction hypothesis as general as possible. So I hope you enjoyed. Let me know if you want me to improve anything. And this is the final lecture of 2021. I hope to see you all in 2022. Happy theorem proving. Merry Christmas. Happy New Year.